Okay, so welcome everyone. It's a great pleasure to introduce our first lecture course. So Rick Kenyon will be speaking about limit shapes for height models. And if you go online on the website of the conference, then you can already access his slides there. So in case if you missed something and want to refresh your memory. With that in mind, let's start. So welcome, Rick.
Thanks, Vadim. And thanks for everyone for coming and the organizers for having me here. Sorry that we couldn't make it to Oxford, but best we can do for now. And there is some construction going on outside my window, so let me know if the sound quality degenerates. I want to talk about joint work with, there's going to be 3 lectures, and the first lecture will be review. Hopefully it won't be completely review for everybody. I hope that there's some new material for at least some people here. But then the second 2 lectures will be more recent material, which I've been working on with Istvan Kraus from University of Eastern Finland. And the previous work is with many people, among them Henry Cohn, Jim Propp, Andrei Okunkov, Scott Sheffield, Jan de Heer, and Sam Watson. Good. And Vadim, you'll interrupt me if there's some questions. All right, so yeah, here's the plan. Roughly 3, I divided the material into 3 parts. I don't know if they will cover exactly 3 lectures, but there might be some overlap. The first, today I'm going to talk about limit shapes. What is a limit shape? What do we mean by a limit shape? And I'm going to give you 2 sort of primary examples, the random partition example and the Lawrence-Challing example. Then I will, most of the next lecture I will talk about general, less probabilistic things, but general gradient variational problems and how to solve them. And then as an application of those results, I will talk about, in the 3rd lecture, the 5-vertex model, which is a special case of the 6-vertex model that Hugo and others have been talking about, and in particular the GINA 0 5-vertex model, which is a slight generalization of that. Okay, so I'm going to start very basic, but you know, if I start talking too fast, please slow me down, otherwise I'll run out of material and we won't have anything to say. So. Okay, so what's a random partition? Well, first of all, what's a partition, right? N is a positive integer, and we want to write n as a sum of smaller numbers. And we write a sum of integers less than or equal to n, right? And we write them in decreasing order, like as shown here. So there's 5 different partitions of the integer 4. 4 is equal to 3 plus 1, or 2 plus 1 plus 1, and so on. All right, and these are, of course, well-known combinatorial objects, and you know, and we've already seen in the talks the Young diagram you can draw. If you have a partition, you can draw a Young diagram of a work partition, and I'm going to draw it in the sort of right side up orientation, French orientation maybe for some of you, right, as indicated here. So the right. There's sort of 3 different possible orientations you can make. There's the American orientation, and the French orientation, and the Russian orientation. But we are going to ask simple probability. The most simple probability question you can ask is, what does a uniform random partition look like? Of course, as we know, there are many different probability measures on partitions. The simplest one maybe is the uniform random partition. And of course, to draw a picture of a random partition, we're just going to make a random, look at the corresponding random Young diagram, which is just a random, it's a collection of boxes, and I'm going to rescale it. I put it in the positive orthant, and I rescale, so maybe so that the area is equal to 1. So here's a random partition of 200. Maybe it's I don't remember exactly how I sampled this one. It was a long time ago, but there it is. You can ask me later how to sample a random partition, but I'm not going to talk about that now. There's a random partition of 2000, and maybe you can start to believe that if as n gets large, there's some sort of shape that these are forming, sort of a limit shape. That is, even though the objects are random and there are partitions which have shapes which are very different from these two, in some sense a typical partition will have a shape which is lying close to either of these. And in fact, that is the content of a theorem originally proved by Virchik and Kirov, or maybe just Virchik, or maybe just Kirov. The history is a little bit unclear about this particular result, but at least it's stated in that paper of Virchik in 1985 that there is a certain limit shape of a large random partition, which we're going to call the Virchik-Kirov curve. And that curve has a very simple formula, which you can see here as just e to the minus x plus e to the minus y equals 1, right? There's the curve. This curve is not quite the curve because it has the wrong area, but if you just rescale the x and y coordinates by some constant, and you can, well, the square root of this constant here, then the area will be 1. It's just slightly more pleasant to draw it in this way without the constant. Okay, and indeed, you can see that if I superimpose the scaled Virchik-Kirov curve with that scaled partition of 2000, it looks pretty close. Okay, so I'm going to spend a few minutes talking about why this is true, how to prove this theorem, because the theorem, this particular proof applies not just in one dimension, but in higher dimensions as well. In particular, we're going to do it in 2 dimensions quite soon. So and also this proof will give you a little bit more information about rate functions and so on. So here's the idea of the proof. And I'm not going to try to make this completely rigorous, of course, but I'm going to give you the main ideas here. And so rather than think about the shape of a uniform partition, let's consider the following problem. Let's fix some curve, which you see. Can everybody see my mouse there? The black curve, which starts somewhere on the y-axis and is monotonically decreasing and touches the x-axis down there. And let's suppose it has area 1 underneath it. And we're going to ask, if I think about a random partition, and I'm going to take a partition of n and scale all the boxes scale it by epsilon so that it has area 1. The Young diagram has area 1. How many such partitions will lie near this black curve? And by near, I mean, let's say within a distance delta in the sort of diagonal direction. So let's fix some small delta, small but macroscopic delta. And now I'm going to scale. I'm going to take my partition of n, where n is so I'm going to take epsilon to be 1 over square root of n, so that the areas match. And I'm going to take a partition, a Young diagram of a partition, and try to fit it inside this little band of width delta around my shape. And of course, when I zoom in to a location along this curve, what I see is that this curve, even though this curve may have a bunch of kinks in it, because it's a monotone decreasing curve, most places will be, the curve will be linear, right? I mean, a monotone decreasing continuous function, a monotone decreasing function will be, differentiable almost everywhere. So for most places, when I zoom in, I will see essentially what's looking like a straight line, as in this zoomed in plot here. And then I have some sort of a lattice path, southeast going lattice path, which follows that line. Here, the zoomed in line is now dotted blue. And so then the question becomes, how many of these southeast lattice paths, which I call broken lines, lie near a given line? And of course, that we know how to do. It's just a binomial coefficient. if I just care about a very small piece of this, what's going on inside this little green circle, then I can approximate the number of curves here with the binomial coefficient, right, which just depends on the slope and the length, right? So the number of broken lines which go from some point here to some point there, that's just a binomial coefficient. And if this broken line has n total steps, that is the length plus the width here is n total steps, and the slope is s here. Well, okay, s, maybe the slope is minus s. Then the corresponding binomial coefficient is n choose n times s over s plus 1, which is, as you all know, it grows like x of n times h of s, where h of s is this particular function here, this Shannon entropy function. All right, so that gives us a good approximation for what's going on locally in this count of partitions. Here's a plot of the Shannon entropy. It's this nice concave function of p, where p is just related to the slope s over 1 minus s over 1 plus s. Okay, so now here's the main idea. You take your curve here. I'm gonna choose some m here, some distance m, which is sort of a mesoscopic scale, like a slightly larger than square root of n, maybe n to the 3/4. And then I'm going to chop up the curve into pieces of width m, and on each piece, on almost all the pieces, my original curve is roughly linear, and so I can approximate the number of partitions which lie near the curve on each piece by this binomial coefficient, which is e to the m times the corresponding Shannon entropy h of s, where s is the local slope, right? So on the ith piece here, there's a certain slope s sub I, and the number of different pictures that I see in that location is roughly e to the m h of si. Okay, so now you're going to have to object that, You're going to have to object that, I didn't take into account the fact that, the partitions have to match up at the boundary. But as long as my m is not too small, these effects are going to be negligible. And that's going to require some argument, which I'm not going to give here, but the width of each piece is much longer than the fluctuations away from as we know, the fluctuations for a binomial coefficient never bring you very, very far from the diagonal, the mean value. And so you can make some small arguments showing that the contribution for the amount of sort of entropy you lose for making these things match up is a negligible amount in this calculation. But then the calculation becomes easy because on each you have a bunch of pieces, like n over m pieces, and on each piece you have a good estimate for the number, and therefore you just have to take the product of these, which becomes the exponent of the sum of m times those growth rates h of si, and of course the si's are just the derivatives of your function f, those slopes. And right. Again, you also have to worry about something about the endpoints, but let's assume for the moment that our curve starts at some place like 0 and 1, some constant there and some constant there. So we're not going to deal with what's happening at infinity here. That's also a detail which can be dealt with. Okay, so then the exponent of this sum becomes, this is of course a Riemann sum for a certain integral, which is just the exponent of n times the integral of h applied to the derivative of f. Right, this is just a sort of a formal Riemann sum for that integral. All right, so modulo these details, which I have, well, probably haven't convinced you that they are negligible, but one can convince myself that those are negligible amounts. The quantity we're looking for, which is the number of partitions approximating this curve, can be well approximated by the exponent of n times this integral. So this is what in large deviations you would call a rate function, this integral of h of f prime of x. Here, remember, h is the Shannon entropy function, and f prime is the derivative of that of your function, the monotone decreasing function there.
Ulrike, I have a question. So in order to make it rigorous, do you need to rewrite this as a function, as some function of function itself rather than derivative? Because you were speaking about being close. Well, being close probably doesn't mean that derivatives are also close.
That's right. That's right. There's some, no, you don't have to use the function itself, but you do have to use the fact that because the function is monotone, it's differentiable almost everywhere. I mean, it's better if you tilt, if I tilted it this way, then it's actually a Lipschitz function in the Russian orientation. And so as long as m is small, then it's going to be well approximated by its derivative on almost every one of those small m pieces.
Okay.
So on all but a negligible fraction of the individual m pieces, this is a good approximation to the result. And then outside of those, you don't gain very much entropy.
Mm-hmm.
Okay, so now let's go back to the original problem. Was we want to understand what happens for a uniform random partition, and well, think about what happens when n gets large here. So the only dependence on n here, n is the length. N is like the n1 plus n2. It's related to the size of the partition, right? So it's like the number of parts plus the number of, anyway, as n, yeah, it's the length of the boundary of the Young diagram. The number of parts of lambda plus the number of parts of lambda star. But when n gets large, this exponential growth rate, any function which has which is strictly less than the maximum value for this integral, is going to be negligible in front of the largest one. So what we really need to look for to find the growth rate of this function is to maximize this integral over all functions f with the correct boundary values that they start here and end there, and have the correct surface area underneath them. So that is the origin of the variational problem, is that we want to maximize over f this particular integral. And by the concavity of the function h, there's in fact a unique maximizer of this function, because if you had two different maximizers, you could take their average. If you had f1 and f2, you could just take the average of f1 and f2, and that would give you an even larger one by the convexity, essentially, or the concavity of h. So there is a unique maximizer, and at that point you can solve. Finding the maximizer, you write down the Euler-Lagrange equation which such a maximizer will satisfy. Now it just becomes a calculus of variations problem. You write down the differential equation which the maximizer will satisfy, and you can solve that very easily, and you end up with the Virchow-Kirov curve. Right, but the interesting thing is that so what you're going to find is that the Virchow-Kirov curve is this curve, which let's go back. It's this one here. It's an infinite curve. It's got, goes, but when you have two fixed endpoints, like there, what you're going to see here is just a part of the Virchow-Kirov curve, which is scaled to go through this point and that point, translated and scaled, and also scaled to have the correct area 1 underneath that curve. So for example, if you wanted a uniform partition with a fixed, whose Young diagram had a fixed starting point here and a fixed ending point there, you would also get a Virchow-Kirov curve, but just part of the curve here. And if you take these 2 points to infinity, then in the limit, you get the full Virchow-Kirov curve. Okay, well, so the conclusion was, maybe I skipped over that too quickly, but the point is that the overwhelming majority of partitions lie near the Virchow-Kirov curve, because the Virchow-Kirov curve is the one which minimizes the surface tension, or in other words, maximizes this integral of the Shannon entropy, which is essentially the growth rate of the nearby Young diagrams. And so this quantity, which I called surface tension, is really just the same as the negative of the growth rate. So when typically, rather than maximizing growth rates, we like to minimize things, and so we define this thing called surface tension, which is minus the growth rate. All right, good. Any questions? There are many other measures on partitions, natural measures. There's the Plancherel measure, which I think we saw in Greta's talk, which also has a limit shape, and I think we even saw Dan on Dan's wallpaper, Dan's wallpaper, his Lego limit shape. That was very cute. Here's another one which is kind of fun. Maybe you didn't know this one. If I take Young diagrams, uniform measure, but I give a weight R per corner in the Young diagram. So if you like, it's the number of it's like R squared to the number of distinct parts of the partition. Then you also get this limit curve now also has a very simple looking formula. And I hope I got it right there, but that looks like that. This is for like R equals 10 or something. So this is a fairly general procedure which works for many different measures. And it also, the same proof that I gave you works in higher dimension too. And there are a few technical difficulties which we had to work out. And this was an original paper by Henry Cohn and Jim Propp. Here's a 3D partition, or plane partition, if you like. This is the 3-dimensional Young diagram of a 3D partition, right? You take a bunch of boxes and you stack them in a corner of a room, or if you like, it's an integer valued function on the integers, which is decreasing weakly decreasing in both coordinates as x increases or as y increases. And if you like, you can again consider the uniform measure on 3D partitions with total volume n. And those also have a nice limit shape, which you can see in the simulation here. And this was originally worked out in the 80s, in 1980 by Nienhuis, and much later by Raphael Serf and myself, because we didn't know about this original result, and also Andrei Kunkov and Kolya Reshetikin around the same time. Here, there's an interesting feature to the limit shape is that even though it extends to infinity in these 3 directions, it is tangent to the lattice planes in the other, to the axis planes there. So it doesn't sort of, what you might expect is that it covers the whole plane, but in fact it has this sort of interesting boundary here, and the curve along that boundary is in fact the Virchow-Kirov curve. There's 3 copies of the Virchow-Kirov curve here, here, and here. Now, once we're in 2 dimensions, however, there are a lot of different possible boundaries. We don't have to just fix, we have a lot more flexibility than just fixing 2 points and considering the curve between those 2 points. Here's another kind of boundary condition where we just take these six sides of a cube and look for a step surface, a stack of cubes sitting, which are constrained to lie inside that cube. And again, this is now called a box plane partition, because box plane partition, where we fix the maximum possible value in each of the three directions, and now there's only a finite number of possibilities if we fix the side length of this cube here to be n, and so we could just consider a uniform measure on all possible partitions of all possible volumes, and this is what the typical shape would look like when the side length is 20. This is, of course, a random Lossless tiling, which I think we saw several times today. Greta talked about it, and maybe, well, maybe everybody mentioned it. Certainly Michael mentioned it. Yeah, so, and the interesting feature, again, here is that you see several different large-scale features in the picture. Near the corners, there's these sort of frozen regions where the tiles are all the same color, and inside it's a mixed-up region, which we call the liquid phase. And this seems to be an interesting feature of many different models. And,
Rick, there is a question in chat from Fabio. He's asking whether there is an intuitive argument why the three curves equal the Virchow curve. So I think that's about probably the result which you attributed to Nienhuis.
Why is the boundary here given by the Virchow curve?
Yeah, I think so.
Sometimes these, I don't know, does anybody else have an intuitive argument for that?
I put something, but it's not intuition, it's calculation. It's just that the marginal on the boundary is a sure measure. And so then, it's kind of the spirit already of things that should be described.
Well, I was going to give a sort of heuristic argument that well, I can't really show you in this picture, but that last curve here, this pink and yellow curve here, kind of gets, in the limit, it gets detached from the other curves. So it doesn't really feel the rest of the diagram, and therefore it's free to do its own thing. And so it's as if it was floating in a sea by itself and constrained to have some volume. And therefore it has to be kind of the Virchow curve. That's the only possibility.
But does it really get that detached? Because it's a continuous limit shape, right?
Yeah, I think that, right, the distance between the, well, okay, yeah, of course it's described.
And the scale of the limit shape.
Some sort of hairy process here. It's a difficult thing. So maybe it's not so obvious. Fabio. Sorry, can't answer your question.
Not obvious that the global constraint on the volume should translate into a volume constraint of the volume of the last layer somehow.
Yeah, it's also a general phenomenon that you can, for other surface tensions, that boundary has a nice shape, which you can get from some sort of limit. But I don't understand that well enough to present it here. So
if I can, so in more generally, do you expect with that that the boundary of these 2D surfaces will also satisfy a variational problem? Is it just a chance here, or is it?
No, I suspect it does.
Okay.
But
okay. Thanks.
It's a completely valid question, and I don't have a good answer. All right. Well, there are many other models which have multiple phases, right? I don't know if you. Here's the. Okay, that was just a silly slide. Okay, so just to sort of summarize here, in a typical surface, if I draw this thing in 3D and I tilt it on the side, you can see that even though the surface is random, a typical surface does lie near this random surface. And what I've been sort of alluding to now is this theorem, which is from 2000, Henry Cohn, Jim Propp, and myself, that, and I didn't make a very precise statement here, but the statement is that there is a unique limit shape. So you take a region in the plane, you take a certain random Lawson's tiling with some boundary conditions, then there is a unique limit shape, and there's a certain variational principle which that limit shape satisfies. And that's what I want to focus on here. The function h, right, whose graph is the limit shape, is going to be the unique minimizer of a certain surface tension integral. Right, so this is now, maybe I can get the, here, let's do this. I feel like I should try to give a teeny bit more precise statement here. So we have some, oh dear, why is this not working? Okay, never mind, I won't do it. Oh, I know what's going on. Try this. Okay, that's not going to work either. I apologize. Let me just say it in words. Can everybody see that?
Your screen is not showing now. Okay, now we can see it.
There we go. Well, yeah, so you take a region in the plane, R, and on the boundary of that region, you have like that hexagon, on the boundary of that region, you have a function, a height function on the boundary, and you want to look for a function on R whose boundary values are determined. And then in this situation, there's a unique limit shape, and it's described by this limit shape formula. And, you know, you have to imagine that this hexagon here, right, has a natural height function along the boundary. As you go around the boundary, the height function is, if you think about the third dimension, it starts at like 0 here and goes up to n, back down to 0, up to n, back down to 0. So it looks like this picture when you put it on edge. And that random surface there, the limit of that random surface is this function h.
Rick, Sanjay is suggesting that if you want to draw something, you can do it on the blackboard behind you, and probably it will be visible to us.
That's a good point. Yeah. All right. If I get desperate, I will do that. Okay, so this is, but now the problem has turned into a gradient variational problem. It's a variational problem. I have to maximize or minimize, in this case, over functions h with given boundary values, this surface tension integral. This surface tension integral is some function sigma, which I haven't told you what it is yet, which only depends on the slope of the function h, just like in the Vershey-Karoff one-dimensional example. All right. But right, and in this paper, we also gave an explicit formula for sigma. It's a little bit more complicated. I'll give it to you in a second. But this kind of variational problem is, of course, well studied in geometry. There are many cases where you have similar variational problems. The most well-known is the minimal surface or soap film surface, right? You have some wire frame. In this case, it's a knot, but you can imagine it just an unknotted wire frame, and you look for the soap film surface which spans that wireframe boundary. It's a very similar problem. The only difference with the previous problem is that the surface tension function that we're dealing with is slightly different. minimal surfaces, the soap film surfaces are minimize the surface tension integral with this surface tension, right? Square root of 1 plus s squared plus t squared, where s and t are the, the x and y derivatives of h, right? The gradient of h has two coordinates, s and t, right? And that's the function that you minimize if you want to find the soap film surface. And the Lawson-Starling surface tension is a different function of s and t. It's a different function than this one, but nonetheless, it's a similar flavor, similar convex flavor. The reason I mentioned the soap films is that there's a beautiful classical solution to this minimization problem, which is called the Weierstrass-Enneper parameterization. And this is really this is a little bit of magic, right? Which says that in order to find a solution to this problem, every solution to this problem can be parameterized by some analytic functions. And in this case, you take your two favorite analytic functions, f and g, and you form this triple of real numbers, the real part of these, antiderivatives, and that parameterizes a minimal surface, which of course depends on f and g, but every minimal surface arises from an appropriate choice of f and g here. F and g, complex analytic functions. So we see that this complex analytic function sort of enter naturally into this equation. And it turns out that the same thing is true in the Lawson-Starling model. There's a parameterization in terms of analytic functions, complex analytic functions. And our goal with Istvan was to sort of understand to what extent this magical parameterization of solutions can be extended to other models. Because there are many other probability models and stat-mech models with this very similar variational problem. Here's some examples. We've already heard about the 6-vertex model today, and it's closely related to the FK percolation model or random cluster model, same thing. And there's also the spanning tree model, which is can be considered to be a special case. All these models have height function interpretations and analogous limit shape problems. So they all have associated gradient variational problems, and the hope is that the solutions to those variational problems can be described in some reasonably explicit way with analytic functions. I mean, you may not be aware, well, I guess the 6-vertex model naturally has a height function interpretation. You may not be aware that just even the basic percolation model, here's a percolation on a honeycomb graph, and this you can kind of see a limit shape arising for this particular kind of boundary conditions for a percolation. So here I'm not taking just a uniform percolation, I'm taking a percolation on a large triangle with certain constraints, certain boundary connection constraints. And the connection constraints are that certain points on the boundary have to be connected across to some other point, and as indicated here. And hopefully you can see there's some sort of roundish shape here, and outside that roundish shape, the model is sort of frozen into these zigzag lines. Okay, so sort of a long-term goal is to understand not just the models which we currently understand, which are the Dimer model, Lawson-Starling model, 5-vertex model, but also the 6-vertex model and these other models. Okay, so let's go back. What I want to do is go back now. How are we doing here? And discuss what the surface tension means in the Lawson-Starling model, so you get some feeling for what's coming. So let's go back to the step surface model, also known as Lawson-Starling model, right? So it's tilings of regions in the plane with these 3 tiles, which here are red, blue, and green. And here you see a tiling of some finite region, maybe it's a torus with periodic boundary conditions. And I'm going to call S the density of green tiles. So the number of green tiles divided by the total number of tiles, and T the density of blue tiles. Right? And S and T, of course, determine, if you think about this as a 3-dimensional picture, the S and T determines some sort of average slope. If this was a torus, right? If I start on the left and I move to the right, then think about how the height function sort of steps down at each green step. So the density of greens and the density of blues determine the height change as you go around the torus horizontally and vertically, respectively. So I'm going to call S and T the densities. Of course, I'm going to call that those are also the average slope associated with this this kind of boundary conditions. And so rather than take the uniform measure on all configurations, I can fix this slope ST and just take the associated measure on configurations which have a fixed average slope S and T. So if you like, fix the total number of greens, blues, and reds to be equal to some fixed numbers, ST, fixed densities, ST and 1 minus S minus T, and then take a uniform configuration with those densities and ask how many are there, all right? And the number of tilings with that density is, again, it grows exponentially with the area, but then there's some growth constant, the exponential growth rate, which is sigma ST, and that is you can think of that as the definition of this surface tension, sigma ST, as the growth rate, exponential growth rate of the number of tilings for the given slope, ST. Right, so that was sort of missing in this statement here. That sigma there is the same as the sigma that I just described down here. Of course, I haven't told you how to compute that sigma ST, but at least this is a definition of sigma ST. And well, you probably know that the Lawson-Tiling model has this nice determinantal structure. It's a free fermionic model, as Hugo was telling us about. So there are determinantal techniques for computing this sigma ST. And in fact, there's a plot of the surface tension sigma, which is now a function of S and T. And of course, S and T are densities, and they sum to less than 1, because the third density is the density of reds. And so the sigma is only defined on this triangle with vertices 0, 0, 1, 0, and 0, 1. And if you like, you can define it to be infinite outside that triangle. And as you can see, it's indeed a convex function that's important for the unicity of the limit shape. All right, so there's another way to, as Hugo mentioned already, there's another way to think about this particular measure. When I fix rather than fixing the densities, I have the option of weighting the tiles. I can put so there's three kinds of tiles, red, blue, and green, and I'm going to put a weight e to the x on the green tiles, e to the y on the blue tiles, and 1 on the red tiles. No reason not to scale the weights so that the red tiles have weight 1. And here x and y are just some real numbers. And then when I weight the tiles, I get a new measure where the probability of a configuration is proportional to the product of the weights of the individual tiles. So I should have said that somewhere, but each configuration now has a weight, which is the product of the weights of its individual tiles. And that you can use those weights to define a new measure on tilings. So for example, if X is very large, then I'm going to tilings which have more green are going to have a larger weight, and so the green will be more prevalent, and that will affect the density of greens. So these X and Y, these quantities X and Y, e to the X and e to the Y, they affect the density. So for each choice of X and Y, there will be, in fact, a typical density, and in fact, there's sort of a concentration of density. So as the system gets large, if I fix X and Y, there will be a unique S and T associated to that. And so the lemma is that once I fix these weights e to the X and e to the Y, and I think about the limit of the system size gets large, the measure arising from these weights is going to be the same as the uniform measure with the constrained slope s comma t. But now s and t are going to be a certain function of x and y, which I haven't told you what that is yet, but that's the content of the next slide. So how do I get from the two variables, capital X and capital Y, to the slope variables, S and T? So these are called the magnetic field coordinates or electric field coordinates, X and Y, and these are the slope variables, S and T. And what I'm indicating from this slide is that there is a sort of a one-to-one. I mean, there's a function which from X and Y will determine the S and T. And let me just indicate the sort of static interpretation of this function. So let's remember that the partition function of this model, if I have a fixed torus, just like Hugo did, is the sum of all configurations of the weight of the tiles, which in this case is going to be e to the ax plus by, where a is the number of green tiles and b is the number of blue tiles. That's the partition function, is the total weight of all configurations. And notice that if I differentiate log z with the log z with respect to x, I will pull down an a and divide by z. This is just going to be the expected number of green tiles. And similarly, if I differentiate log z with respect to y, I get the expected number of blue tiles. And if I then divide by n, the total number of tiles, then what I see is that this quantity log z divided by n, the free energy, has derivatives, x and y derivatives, which give me the densities. So this, you can think of this as the sort of how x and y are related to s and t. They're related through the fact that the free energy derivatives with respect to x and y are s and t. And one can likewise show that this quantity, this free energy, which is the limit as n gets large. Well, okay, I made a mistake here because the free energy is really supposed to be the limit of this quantity as the system size grows, capital N grows. And in that limit, the free energy is the Legendre dual of the surface tension sigma, in the following sense that well, free energy f of xy is equal to minus sigma, oh, that should be a t there, minus sigma st plus sx plus ty. Where s and t are related to are equal to the derivatives of the free energy with respect to x and y. And in particular, this Legendre duality is a duality, so you can, in fact, invert the relation, and the s and t derivatives of sigma are give you the inverse map, which goes from s comma t to x comma y. Are we okay? All right, so this is a little thing I'm going to use in a moment here. So let's go back to this variational problem. Hopefully I've at least explained the appropriate objects that come up in this variational problem. How do we actually solve the variational problem now? Well, right, we need to minimize this surface tension integral, and associated to such a minimization is a differential equation called the Euler-Lagrange equation, which perhaps, you know, this is a standard calculus of variations technique, right? To minimize this integral, you write down the function h that you're looking for will necessarily satisfy a certain PDE. In this case, it was an ODE in the case of the Virchow-Kirov curve. Here it's a PDE, and that PDE is reasonably easy to write down just from the formulation here. And it looks like the following. It looks somewhat complicated. This is you take the function h, its gradient, you apply the you look at the gradient with respect to S and T of sigma, there you get this vector field. You look at the divergence of that vector field with respect to X and Y. That needs to be set equal to 0. That is the PDE. It's a kind of a nonlinear PDE in two variables. But if you think about the definition of capital X and capital Y, which are the S and T derivatives of sigma, this PDE looks much simpler. It's just the little x derivative of capital X plus the little y derivative of capital Y equals 0. Here, little x and little y are the coordinates on the plane where your height function is living over. Right? Remember, H is a graph of a function of these two variables, X and Y. And so this PDE says that these two quantities, capital X and capital Y, which are of course functions of sigma, well, the derivatives of sigma, they satisfy this very simple equation. So now, before I tell you more about how to solve that equation, I'm going to, because this model is just one example of a whole family of examples, I want to talk a little bit about general gradient models. And this is already getting into the next talk a little bit, but that's okay, unless there's some questions.
Rick, there was a question from Fabio. So he was asking about this percolation model that you were showing. Like, how did you find height function there in order to make this formulation?
This one.
Yeah.
Right. The way to find the height, well, okay, this is a little bit outside of what I want to talk about, but you can just orient these curves. I mean, I guess the simplest way to do it is to use the correspondence between the 6-vertex model and the FK percolation model, or the percolation model. And the 6-vertex model does have a height function associated to it. Alternatively, you can sort of do directly by just orienting these blue curves from right to left, or maybe you take the white regions, which have a sort of a orientation from one side to the other. Of course, you can't really be consistent about this orientation, but at least locally, there's a well-defined height function which changes by 1 when you jump from one white region to the next region. Did that help at all? You don't need, it doesn't have to be a height function. All it has to be is a function which depends, in this case, you have this sort of lamination by, or if you like, some sort of discrete version of a foliation into pieces, right? Each of these components, like this component here, right, runs horizontally vertically from one side to the other. And if you squint your eyes, you can count the number of components in any little box. And that count, so the number of components has both a direction and a density. And those are the two variables which you use to define the corresponding measure.
Rick, how was this configuration sampled again?
Did you understand the concept?
Or what was this measure on this triangular?
Okay, yeah, I take percolation and I constrain it so that for every point on the boundary here, it's in the same component as a point across there. So points here are connected there, points here are connected across there, points here are connected across there. And there's one point right in the middle which has a triple connection, if you look carefully. Mm-hmm. This component here is connected to exactly 3 boundary components. Other than those constraints, it's a uniform percolation, uniform edge percolation on the honeycomb grid. And there is a way to sample this, to do an exact sample through some recurrence, kind of like the Q recurrence, which I'm not going to talk about here. I can tell you about later. That's where this problem came from originally, is through some sort of algebraic Baxter equation, which sort of spits out this picture sort of for free, but then you start to ask, is there some sort of limit shape here? This is like kind of like the Aztec diamond for honeycomb percolation, if you like. All right, let me just say one or two more slides and then we'll stop, because apparently I don't have a good stopping point here. But there are gradient models. What is a gradient model? It's a variational principle where the surface tension only depends on the gradient. Right, so there's a surface tension sigma, which is defined on some region in the plane. This is something in 2 dimensions. Takes real values, and it's assumed strictly convex and smooth. And so in the Lawson-Tiling case, this n is just that triangle, the unit triangle. But for other models, even other diamond models, n can be some arbitrary domain, even the whole plane. So the first sort of geometric viewpoint here is to think about a certain metric on n, and because sigma is strictly convex, it has a positive definite Hessian matrix. It's smooth and strictly convex. So you look at the Hessian matrix, the matrix of second derivatives, and here the coordinates on n are s and t. Those are the slope variables. I hope that was clear, right? Remember, let's look at this picture, right? Think about this picture, right? There's the s coordinate there and the t coordinate there. Those are my 2 coordinates, and here sigma is some nice strictly convex thing. Think about that picture. Now, it has a Hessian matrix, a matrix of second derivatives, and from that entries in the Hessian, you can make a metric, a Riemannian metric, right? Sigma SS, sigma ST, sigma TT. Those define the entries in this metric G. That's a metric which lives on n. The space of slopes. In fact, here it is, the space of slopes, right? But you have to remember also that I talked about the free energy, capital F, and the free energy is the Legendre dual of sigma, which means that the free energy lives over here on the xy plane. It's also a convex function of x and y, and the gradient of sigma, because these are Legendre dual functions, the gradient of sigma maps the region n over here onto the xy plane, and the gradient of sigma is just the inverse of the gradient of f. These two maps are inverses of each other, so really there's well, it's not a bijection in general, but at least there's a map from n, which is, in this case, the image is the interior of this curvy shape here, which you might recognize as sort of the boundary of that 3D Young diagram. It's called the amoeba here. The amoeba is the image of n under the map grad sigma. Right, so on n we define this Riemannian metric over here, but we can push that metric over under the map gradient sigma over to this side, and it gives you a metric on the interior of this, on this set here, A, the amoeba, which, if you like, you can define it just from the Hessian of the function f, right? Over here, I can use the Hessian of the function f. Over there, I can use the Hessian of the function sigma, and those define, in fact, the same metric there. This is an isometry between the metric space here and the metric space there. That's what this statement says. On the amoeba is the image over here. The Hessian of f also determines a Riemannian metric, but the map going between the two is just an isometry. So you can think of them as the same metric space. Right, so this metric is somehow important for us, and maybe I'll just stop on this slide here and pick this up next time. There's an important theorem which is extremely old, goes back to Gauss, that you have a metric on a two-dimensional smooth Riemannian metric on a surface, there's a what's called an isothermal coordinate, or a conformal coordinate, if you like, a z, which you can write in real and imaginary parts, u plus iv. Sometimes u and v are called the isothermal coordinates, in which the metric becomes a diagonal, just a scaled copy of the Euclidean metric in these coordinates u and v. Right? And so the punchline of the next talk and the talk on Friday is that this coordinate is going to be the conformal coordinate which controls not just the limit shape theory, but also conjecturally controls the fluctuations of the random surfaces here. So that's sort of the important point to realize, is that there's sort of a natural conformal coordinate, and how does it arise? It arises from this Hessian of the surface tension. Okay, so maybe this is a place where I will start next time. So let me stop now.
Rick, so in principle, you have 10 more minutes if you want to continue, because the talk is formally 1 hour, 15 minutes, but it's up to you if you want to stop here.
Well, I'm happy to have people ask questions for some time, so I don't want to
Okay.
go over too.
Okay, then thank you. So how about questions? Are there any questions about anything? Feel free to unmute yourself and ask questions. Rick, the theorem of Gauss, you apply it to the coordinate system on the triangle?
Yes.
Okay, so that's just
Yeah, so you can think of, on this triangle, there's a certain conformal coordinate z. So you can think of z as living in some maybe disk or upper half plane, and z is a map from the triangle to the upper half plane. So some standard conformal surface, like the upper half plane, right? Once you have one conformal coordinate, then you can apply any analytic function to get a new conformal coordinate, any Riemann mapping. So we get to decide what domain our z takes values in, but we might as well choose it to be the upper half plane or something.
all right. But
standard domain.
Up to this conformal transformations, is this Gauss theorem, is it unique choice, or is it, well, there are many choices actually?
No, there's only one choice.
There's only one choice.
Yeah, sorry. I'm getting a little bit ahead of myself, but there's the two-dimensional Riemannian metric determines a unique conformal structure. There's a unique up to conformal transformation. There's a unique up to conformal transformation choice of conformal coordinates.
Mm-hmm. I see.
Can I ask a question? Hi, Vadim. Maybe I can also put my video. I have a sort of, I was off by 1 in my calculations to join this talk. Will the slides be made available? Are they on your website?
Yeah, I think that Ivan, I sent them to Ivan and he gave a link somewhere.
So they're already on the website of the conference. If you go there.
Which website? This web EUR or?
Yeah, exactly there. So you go there to the mini course program and you click on the Rick's lecture, and there is a link there, access the slides here, and you click on it and you get in slides.
Ah, okay. So maybe they were uploaded recently, or maybe I haven't refreshed the browser. Okay, I see. Cool.
So I have a question, Rick.
Yes.
You mentioned that the spanning tree model has a limit shape. What is that? Which model are you thinking about?
Yeah, so that's right. I can kind of go back to this picture again. You probably know the version of this picture which uses groves, which comes from the cube recurrence. Have you seen that?
I may have, but I have forgotten if I have.
Yeah, so the uniform spanning tree measure on a on the square grid is just one measure in a 2-parameter family of measures on spanning forests, where the spanning forest has essential spanning forest, which has a sort of infinite number of components, a certain density of components, all going in a certain direction.
Yeah, I remember that now.
Yeah. So that's the family of measures that I'm thinking about. And if you have some picture, kind of like the one indicated on this slide, where instead of doing percolation, you do spanning forests, where each component has to connect to boundary components in a somewhat similar manner. Then you can ask, then there will be a similar limit shape phenomenon and the variational principle which describes that limit shape phenomenon. This is in fact worked out by Dave Spire and Peterson, who was it, Carroll and Peterson. They give this Arctic circle theorem for groves. I don't know, you may remember that paper.
I don't.
In the 90s, that was one of the first examples of a limit shape after the Aztec diamond limit shape, and it involves spanning forests. And so there's a certain variational problem which is very similar to the Dimer variational problem, which describes those limit shapes.
Okay, thanks.
I can send you the reference if you would like.
Okay, sure.
So there is another question from Sanjay in the chat. So it reads, the map from the Newton polygon to the amoeba is an isometry in the triangle case. What happens for general Newton polygons?
It's always an isometry.
Okay.
Yeah, it's an isometry. That's a general fact. It's not just about the Dimer models. It's for every gradient variational problem. There's a notion of, you have the surface tension. It's Legendre dual is the, we might as well call that the free energy. It's not called that in general, but the Legendre dual is the surface tension. Has this property that the metric you define on one side is isometric to the metric you define on the other side. This slide is a general fact about variational problems, gradient variational problems, not just about static models.
Is this in any genus or just genus 0 for the amoeba?
Yeah, here genus 0. I mean, there are versions of that statement for a higher genus, but just for simplicity, I think we should consider the case of genus 0. So both sides are sort of simply connected. But it's an isometry in both cases, in the higher generality. Right. If there are some, for those of you who know it, in more complicated Dimer models, there are some interior singularities here where the surface tension is not smooth, and those, of course, on the right-hand side will correspond to sort of holes in the amoeba, but outside of that, in the sort of so-called liquid region of the amoeba, the map is an isometry. The metric is not even defined across the boundary because it's not smooth.
Okay, do we have any more questions to Rick?
Yeah, may I? Hi. Yeah, just to go back quickly on this percolation thing, I'm not sure I understood. Like, do you just say that you sort of take inspiration from the Grove case, or do you claim that there is also a discrete equation there?
Yeah, this is definitely an exact simulation of this configuration, which I made from some recurrence, a certain recurrence arising from the Yang-Baxter equation for the percolation model on a triangular grid.
I see.
Right. As Hugo described, there's a, I think he said that there's a certain Yang-Baxter equation. Yeah, he did. There's a Yang-Baxter equation for a 6-vertex model, of which percolation is a certain special case. Maybe he'll talk about that in his next lecture. And you just like you do in the Aztec diamond or in the Grove case, you start with a certain configuration and you you make this recurrence, this outward growing recurrence, and you get a shape like this with certain boundary connections.
So you claim that you can transform like the percolation star triangle into a single polynomial thing.
And can you ask the question again?
Yeah, so you're saying that you're looking at this star triangle, say for percolation, in just the right way to make it a single valued recurrence, right?
Single valued recurrence.
Yeah, I mean, usually it involves, you know, several, say, edge variables or something like that.
Yes, if I understand you correctly, you know, there's a single recurrence which we start with a certain percolation configuration, and you, just like you do in the Aztec diamond, you start with a certain dimer, right? There's a shuffling algorithm for percolation. Maybe I can say it like that. This is the result of a certain shuffling algorithm for percolation, just like the shuffling algorithm for domino timings. Whereas you start with a periodic configuration, then you shuffle, 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 and you get the Aztec diamond. Or you shuffle, 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 you get this triangular shape.
Right. I was just curious about like the form of this particular one. But sure. Okay.
Well, I can tell you about that offline maybe.
Sure. Thank you.
Sure.
So there is yet another question in chat from Anthony. It says, in which scenarios is it preferred to use the 6 vertex model over the spanning tree or the FK percolation models?
That's kind of a vague question. Well, we'd like to think that they're the same, but of course they have some important differences. The 6 vertex models feels like the most general one, but if you want to make these nice pictures, somehow the percolation models are more adapted. Right? If you want to talk about, you know, probabilistic aspects, somehow that FK percolation seems like the place to work. But the sort of, in terms of the exact calculations, we always have to go back at some point to the 6 vertex model, transfer matrix techniques, and so on. I'm sure I'm not answering your questions, but it was kind of a vague question, so maybe that's okay.
Is there any notion of correlation functions for this model? 1-point correlation function or some such, maybe 2-point?
Yeah, absolutely. You're talking about the model that's displayed on the slide.
Yes, precisely.
Yeah, of course. I mean, you can see that the behavior is very different near the corners. So you can ask, what's the probability of a horizontal edge near the right corner goes to 0 exponentially fast?
But it's not determinantal, right? I'm correct in saying that the model.
That's correct. As far as we know, I'm sure it's not determinantal, and nobody really knows how to compute this. I don't know how to compute the limit shape in this model because I don't know the surface tension. I think that's an excellent open question, but you know, it's probably just as hard as finding the, you know, free energy for the 6 vertex model in the most general 6 variable, you know, asymmetric case.
So are you saying that this inscribed, which looks like almost like a circle, it's actually unknown? What is the exact shape of this?
That's correct. It's unknown. And I don't think it's a circle. It's probably not even analytic. It's probably piecewise analytic. Given what we know about this 5 vertex model, it's a piecewise, 6 vertex model, it's piecewise analytic curve.
Okay.
I guess I could have given a whole talk about this particular figure. If people are excited about it, I can prepare a different talk tomorrow. No, I won't do that.
Okay, if there are no more questions, then let's maybe thank Rick again. Thank you for a beautiful talk. And Rick will continue tomorrow. And for today, I think that's it. So have a good rest of your day. Bye-bye, everyone.
And Michael will start at 9 a.m. tomorrow. So we'll see everyone bright and early. I'm going to end this session.